Hi, in today's video I want to introduce a software development practice called test-driven development, a practice that originated from the extreme programming methodology and that is often used in software craftsmanship communities as a first-class practice in day-to-day development. Test-driven development is often referred as TDD. It's a very simple idea at first glance. You simply write the tests for your program before writing the program itself. In doing so, the advocates of test-driven development are promising a land of benefits that many beginners in TDD are having difficulty to find or make a reality. So today, we will explore our own journey from scratch to finish with a test-driven project, and we will answer those questions. Does TDD yield to better design? Does TDD prevent bugs? Does TDD slow us down, and by how much? Is TDD the holy grail of all practices? Let's figure it out. There are actually different flavors of TDD that exist. In today's video, I will focus on a specific style of TDD called Classic TDD, and I will dedicate other videos for the other style that exist. Classic TDD is a style of TDD that is also sometimes referred as Classicist TDD, Detroit School of TDD, Chicago School of TDD, or State-Based TDD, especially when compared to its little brother in UK, the Outside-In TDD, Mockist Style TDD, or London School of TDD. If you have been exposed to a test-driven development in any training session, chances are you have been introduced to a classic style of TDD, as it's a very popular style, and that is often the first one taught to beginners when experimenting with the benefit of the practice. To explore how we code in TDD, we will use a simple exercise, the Mars Rover Kata. If you have no idea what is a coding kata, you can find lots of them online. I will provide all the links in the description. Coding kata are inspired by the Marshall kata, and are simple exercises that you can use to put a specific focus on what you are trying to learn. For instance, you can use the same kata to learn about communication and pairing in a group. You can use a kata as a way to work on your IDE shortcut efficiency. You can also use a kata to approach a problem with a different paradigm of language, or as today, you can just simply use a kata to learn a practice such as TDD. For the sake of keeping things simple, I will just use a lighter version of the exercise displayed on the screen. And I will only use one rover to manage, and I will not use any wrapping over a grid or no obstacles. I will provide initial place and orientation to the rover and send a set of commands to it. Today I'm going to use .Dotnet from Linux, starting from scratch, but really, if you use any other object-oriented language, you should be able to follow along the different steps that this video is going to demonstrate. Okay, so let's start. I'm going to create a folder to host my solution, and I'm going to call it Mars Rover. Once the folder is created, I'm going to go into it and create my initial solution. Once it's done, I'm going to create two projects. The first one is going to be my main project. It's going to be a console application in that case, and I'm going to call it Mars Rover simply. Once it's done, I'm going to create the second project, which is going to be an XUnit project, and that's going to hold all my assertion, my tests. And I'm going to just name it marsrover.test. Okay, so now we have the two projects. As a matter of taste, I like to write my assertion the closest I can from the natural language. So I'm going to use a package called Fluent Assertion that helps write the test in a more natural language fashion. And I think the current version is 5.10.3. And finally, my test project will need to reference the production project, the main project. And so I'm just adding here the reference. Now I need to add these two newly created projects to my solution. I'm adding a simple git ignore provided by .Dotnet CLI, and now I'm able to create my git project and add all the files newly created. Alright, now I'm going to open my solution in my IDE. Here I'm going to use Rider. I'm going to enter the presentation mode so that you can see clearer what I'm going to type during the exercise. And as you can see, we have basically two solutions. The first one just has a simple program with a hello world, and the second is a test project, which is just an empty test class. You could either delete the test and create a new one, or just simply rename it, which I'm going to do here. I'm going to use here the convention terminating the test class by should, so that it treats like Mars Rover should do something. And in that case, the simplest thing I can think of is just print the initial state when you don't do anything. Keep in mind that when I am naming things like state, I'm already defining my domain model, so be careful when you choose your variable name. The classic structure of a test class is divided in 3 main parts. The first one would be arrange, where you put your setup, act, when you really act on your unit, and assert, where you verify the behavior of the unit you are testing. This map quite naturally with the Gherkin language, where you name things like given, when, then. The Gherkin language is a very popular way to write acceptance criteria for your user story, so it makes it quite easy to translate the acceptance criteria into your test. I will start my setup with a Mars Rover object, in which I will inject the initial state. Here I'm going to start from the center of the grid, pointing to the north. For the act, I will take a result back from acting on my Mars Rover. The result of the execute empty command, which would be here an empty string. And finally, for my assertion, I will verify that the result of this execution is basically the initial state I started from, which is basically the center of the grid pointing to the north. I cannot execute my test yet because the Mars Rover class does not exist, so I'm just going to add the Mars Rover class here, and I will fix the compilation error, a constructor for the initial state, an execute method that will take my commands, and finally I will import my Fluent assertion library to run the test. Alright, test is failing as expected, but it's important to always check the message of your exception to verify that it's failed for the expected reason. So here, for instance, it's complaining about receiving an empty string instead of the expected 00n, and the simplest things to do to fix the test is return 00n. So the test is now green, and we can enter the third and last phase of the TDD cycle, which is the refactoring phase. And in terms of refactoring, we can here extract the class in its own file and move this file out of the test project into the main project. We have just executed the 3 phases of the classic TDD loop called the red, green, refactor loop. We provided the smallest implementation possible to pass our test, but we know that our implementation is actually only successful for one specific position. To force the implementation to be correct, I need to write a new test from a different initial position. This process is called triangulation and is fundamental to the classicity style of TDD. Here I would write a test starting from a different position, let's say 2, 1 and pointing to the west. And I would expect my final state to be exactly the same, 2, 1 pointing to the west. As expected, they fail because we return a hard-coded string. And the smallest change I can provide to pass the test is to return the initial state. The test is now green and I can enter the refactoring loop. Test, like production code, should be looked into during the refactoring phase. Here, for instance, I have 2 tests that test the same things with different parameters. Instead of having 2 tests, I would simply refactor my test to be parameterized. I am refactoring the test to get the initial state as a parameter of the method. I verify that the test is green, and now I can use one single method to test both initial state cases. It's green, and I can now delete the duplicated method. So we have now a successful empty command feature, and I know I don't need to triangulate any further my test to return the right value. I can now implement a new feature, and of course I will need to write a test to do so. We can try, for instance, to send a single move forward command and test that the rover returns the right position. Just like for the other test, I will need a Mars Rover object, and I can start from any position. And I will act in the same way by sending a command, but this time with M. And I will verify that my rover has moved by 1 unit on the y-axis, which should bring him to the coordinate 0, 1, n. The test is telling us that our rover didn't move, which is normal as we didn't implement the feature yet. And so the simplest thing I can do is hardcode the expected return value if the command that is sent is M. The test is now green, but to force the correct implementation, I will use triangulation by adding a new test case. And to do so, I will directly refactor my test to be parameterized. I'm adding now a new test case, but this time starting from position 1, 1. And the test fails, returning us the hard-coded value we just implemented. So now the next thing to do to really return the correct value is to parse the initial state so that we can increment the y-axis. So for that I'm going to split my initial state with the colon character. I'm going to take the integer value from the first slice. The integer value for the second slice for the y-axis, and finally the direction will be the third slice of this string. And now I can just return a parameterized string with a value y plus 1. Great, so moving nose is now implemented, and we can try another case, and we can move maybe west, and it will basically make us move 1 unit less on the x-axis. The easiest things to do here is to add some if statement to have conditional return depending on the direction the rover is pointing to. So we're gonna basically keep the north return that we implemented before, and we're just gonna add after that a direction west and decrement the x value before returning it. So with this new case, we can see a major pattern in the value we return, and we can take advantage of that to refactor the last return statement and to make it more aligned with the states that we return, so returning x, y direction instead of the initial state. And this enables another refactoring, which is removing the return value and mutating the x and y variable, which express much better intention than the complicated return statement that we had. There are other bits and pieces that we could tackle here, but we're going to delay it and just introduce a new test case before putting our attention on this refactoring. So this time we're going to direct the rover on the east direction. We should move the rover 1 unit more on the x-axis. So the test is failing, and the easiest way to fix it is just returning another conditional with the if statement and increasing the x value for the east direction. We are now green, and clearly this if statement that is just depending on the direction is actually a switch case. And switch case in object-oriented language is a common code smell, and is your code basically yelling that you're lacking polymorphism. If you have no idea what is code smell, I will link some websites that reference most of them, and they're basically good indicator of something doing wrong in your design. So here, for instance, the switch statement is listed as one of them, and basically is telling the same thing, which basically you're lacking polymorphism, and it even gives you some hints about how to tackle the refactoring of it. They're suggesting like moving and extracting method, and investigating using a state strategy, which is exactly what we're gonna do. Before starting extracting any method, there is another code smell called primitive obsession that I need to tackle. This is done in several steps. I move the local variable into their own fields, and once it's done, I can extract a class here called position, and make the fields of position public so that I can access them directly from my class. Now I can extract my method, and they will all act on the same object, position, instead of the individual x and y that they were previously acting on. As you can see, after each refactoring, I keep running my test to verify I didn't break anything. At the moment, this method is coupled with my class because it mutates a field that is private to this class. To be able to extract this method to other classes, I need first to remove this dependency to the field. So I will return the position on each of the method, and I will also pass the position as a parameter. Even if it's not yet necessary, I will reaffect the position field with the return value from the move method, so that I can later on return new values instead of mutating the internal fields x and y of the position class. Okay, so now as the ID is indicating us, the methods are completely independent from any field from the class and can now be made static. And the static method, being completely independent, can be easily moved to a new class. So I'm going to extract a new class called East, another class called West, and finally a class called North. I will change the visibility of the method to make them public. Now that each individual class holds an information about the direction, I can rename each function with a similar name, move forward. We can see slowly here emerging the polymorphism that we were wishing for. So the next step here is to create a common interface called iDirection that each of the newly created class can implement. So now this function don't need to be static anymore, as it can be a method called directly on a new instance of the direction class. The three different methods are no longer static and they all share the same signature, so they can be bumped upward into the direction interface. Now that we have introduced the right polymorphism, we need to introduce the right amount of duplication so that we can extract things from the switch case. To do so, we will extract a variable here. I'm going to call it direction, and I will make it a field. I can now repeat the process for the other direction, pointing to the same field. And now I've introduced what we call pure duplication, which is the simplest things to refactor because you can easily extract it from the switch case. I can now extract a method for the first block, which is basically a direction factory. And as previously, I will try to make the function independent from any field so that it can be static and extract to another class. Finally, we can finish the refactoring by moving all the created classes in their own files. I can now add the last test case to move forward, which is moving in the south direction. And now that I'm in the refactoring phase, I can address a previously mentioned annoyance I had with mutating the internal state of position, and I will instead return a new instance of position with a new coordinate. By doing so and refactoring to expression body, we can clearly see emerge the state pattern strategy that we mentioned previously. Now, the last remaining thing that prevents us to make our field read-only is this empty constructor. So getting rid of it should enable us to make our field read-only. We have now finished implementing the move forward feature. We can create a new test for the next feature, for instance for turning right. But instead of creating a new test, I can see some duplication between my tests and an opportunity to refactor them. They both do almost the same thing except for the commands applied. If I pass the command as a parameter, I should be able to test all cases in one method. We can now test the turn right command by adding a case on our execute command method. Here we will test that the rover pointing to south will point to the west and stay in the same position after turning right. As usual, I will focus on the easiest implementation first, which is returning the hard-coded value if I receive a R command as a parameter. And I will let the triangulation process force me to generify my implementation. So I'm going to add a new test case. A rover pointing to the west and turning right should be pointing to the north. This will force me to have two execution paths depending on the direction when I receive a turn right command. One for the south and one for the west. We are now in the refactoring loop, and I am annoyed that I could not act on my direction object model, just because the current implementation returns the initial parsed string called direction string command. Ideally, this direction string command should come from my domain object. So I'm going to add a asString command on my direction class. I will not use toString because this single letter representing the direction may have a meaning in my domain, and I want to properly express that. It looks like I have broken something. Luckily, my tests are able to tell me right away. And indeed, now that I'm returning the value for my direction object model, that direction needs to be created outside of the specific execution path for the move forward command. So now, instead of returning hard-coded string, I can mutate my domain object's direction. But we know now that the sequence of if statements that are emerging here is a sign that we should use polymorphism. I already have a class to act on, so I'm going to move the implementation of turn right to my direction class. I am only going to provide the implementation for the south direction that I'm currently working on. And repeat the process for the west direction that is already tested and verify that my tests are still green. Here again, we have a very clear state strategy pattern that emerged from the refactoring. And now we can add the other test case to cover the two other directions. The turn right command is now fully implemented. I can now implement the last command, the turn left. I'm going to break one of the rules of TDD here by adding several breaking tests at the same time. I am only doing so because I know exactly what the implementation will be and I know they will be fixed very quickly. Our turn left command is now fully implemented. The only remaining bit to be feature complete for the Mars Rover exercise is to support several commands and not a single one as we tested until now. So let's add a test to cover this. And this is it, the Mars Rover project is now feature complete for our exercise, but we still quite have a bit of refactoring to address now. We notice here a sequence of if statements, which is always a bit of a code smell. These statements mutate two different objects at the moment, preventing us to generify the action, the direction and the position. These two variables though, when we think about it, belong to the same concept, a rover. So let's extract a rover class to encapsulate these fields. We can extract some methods to describe the actions. And because this class only depends on rover fields, they can be moved to the rover class easily. As with position and direction, we will let the rover class return a new state, which should enable us to make all fields read-only later on. I can now extract this block of code as a create rover method. Finally, we can see that for each individual command character, we execute a different method. This calls for command pattern refactoring. Here, we inline the moveForward method, which replaces the call with the implementation, hence transforming the moveForward call to a command creation and an apply to the rover. We now do the same for the turnRight method. Finally, our last refactoring will be to remove our dependency to the individual command characters by building a list of commands first and then applying them to the rover. Now let's give a final look to our project and clean up the bits and pieces that we find. So let's conclude our TDD exercise. As we can see, classic TDD can lead to very structured code and highly cohesive objects. Nevertheless, the emerging nature of the design will be only as good as your refactoring skills. You will need to be able to identify code smells and know how to refactor your code through baby steps while always staying in the green. If you manage to do so, it is very pleasant to always know you are always working on a fully functional code while seeing your design emerge. Classic TDD can be complicated in more constrained environment like existing project with responsibilities already laid out in different classes. In such case, the outside-in TDD would be a better fit, but that is a video for another time. Bye for now.